Hi, my name's Peter. You may have seen me on the discussion board under the name Coranda. In this video I'm going to tell you about my entry in CECC4, but first I'll give you a little background about myself. Unlike, I suspect, most of the people enrolled in 6002, I'm not at the start of my career but rather at the other end. When I was at high school in the early 1970s, I had a hobby interest in electronics, and I used to buy magazines like these and build projects that they published. Of course, all I was really doing was assembling a kit that someone else had designed. I never had any real idea of how they worked, and if something went wrong, there wasn't much I could do to fix it. Well, I recently retired and decided that I wanted to rekindle my interest in electronics. I had a fairly strong software background, mainly in business systems, but I thought a good way to get started would be to start dabbling with a microcontroller like the Arduino and see what I could make it do. That was fun, but after a while you get sick of just reading buttons and flashing LEDs, so I wanted to try something more ambitious. To do that, I was going to have to understand a lot more about analog electronics, and, luckily, I found this course. It's taught me an enormous amount and given me the confidence to, for the first time, design my own project. Now, I like to cook, and when I do, I make use of my old faithful kitchen timer. It's a pretty simple clockwork mechanism. You turn the knob, set the time, and it counts down and rings. The trouble is, as you can see, wear has taken its toll and it doesn't work properly anymore. Now, the smart thing to do would have been to spend $10 and buy a new one, or just use the app on my phone. Nonetheless, I decided this would be an interesting first design project. What I've produced is probably overkill for the job, but it was just a learning exercise, a great learning exercise, and gave me the chance to put some of what I've learned in 6002 into practice. So, I'll take you through some of the main aspects of the design. Here's the basic design I wanted to build, although it got a lot more complicated and interesting as the project developed. The device needs a way to enter the timer value. I chose to use a rotary knob because it's reasonably compact. It needs some way of displaying the timing. I chose a pair of LED digit displays. That would give me up to 99 minutes, which is more than the mechanical timer it's replacing gave me. And of course, it needs a button to set the timer running. Now, rather than using a potentiometer to set the time, I chose to experiment one of these. It's a rotary encoder. It has indents as you turn it, and it makes it easier to set the time more precisely. It requires about 5 complete turns to cover the 1 to 99 minute range. It also has a push button switch built into the shaft, so it can serve as the run button as well. The rotary part is quite simple and clever. It's basically a pair of switches that send out pulses as the shaft is rotated. But the pulses from the two switches are 90 degrees out of phase with one another. This means that, for example, if we wait for the left channel to go high, then immediately read the state of the right channel, we can use the right channel state to tell whether the encoder was turned clockwise or anti-clockwise. The problem was that when I tried this, it wasn't as reliable as I'd hoped. It seemed that it worked sometimes, but at other times one click of the encoder would be read as several clicks. I decided to have a look at the pulses, and so I built this simple test circuit. The switch is one of the pulse switches in the encoder. The D pin is where the microcontroller would read the pulse, but in this case I connected it to an oscilloscope to see what the pulses looked like when I rotated the encoder. This is what I got. We can see the train of pulses here, which is what we would expect, but if we look closely at some of the pulses, we can see the problem. In this case, the switch is closed and rapidly reopened, then closed again several times. A little bit of research revealed that this is a common phenomenon called switch bounce. It's talked about in the Arduino community and is commonly dealt with in software by reading the pin multiple times over a few milliseconds to make sure it is stable. Now, I could have easily solved this problem in the code, but my objective in this project was to learn more about electronics, so I was looking for a hardware solution. What I wanted was a system where, once the switch had closed and dragged the microcontroller pin down to ground, reclosing the switch would delay the pin from rising back to VIH, and preferably not beyond VOL. And in 6002 we learned that the circuit element that resists sudden changes in voltage is the capacitor. So I tried this simple circuit. In parallel to the switch is a damping resistor and a capacitor. The damping resistor is probably not strictly necessary in this project, but it should be some relatively low resistance, say 100 ohm, that limits the spike of current flowing out of the capacitor when the switch is closed and that capacitor discharges. Now when we look at the pulses on the oscilloscope, we can see that the system responds quickly to a closing of the switch, but when the switch opens, we see the classic exponential form. Choice of component values isn't too critical. Often the pull-up resistor will be internal to the microcontroller, and design is about choice of capacitor. You just need to make sure that when the switch opens, it will take longer than the duration of each bounce pulse to rise to VOL, but that the rise time is not so long that it will not have made it up to VOH by the time the next pulse comes along. The maximum rated rotation speed of the encoder, according to the spec sheet, is twice per second. Given that each rotation has 20 indents, that's a frequency of 40 Hz, which is a period of 25 milliseconds. In this case, VOL is 0.9 volts and VOH is 4.2 volts. We can calculate that the time taken to rise to these voltages, given a 5 volt supply, as approximately 0.2 and 1.8 time constants, respectively. In this case, the microcontroller spec says that the pull-up resistor is in the range 20 to 50k. I used a capacitor of 100 nanofarads because I happen to have a few of them on hand. This means that the rise time will be 0.4 to 1 millisecond and 3.7 to 9.2 milliseconds, which is what we're looking for. The next issue faced is how to control the LED digits. They are just an array of ordinary LEDs, so they could be controlled through software the way any microcontroller drives LEDs. But there are a couple of problems with this. There aren't enough available pins on the microcontroller for the 16 LEDs. The microcontroller might struggle to provide enough current to drive all of the LEDs at once. And after all, I'm trying to learn about hardware, not software. So I toyed with the idea of building a network of gates that could do the job, but that looked far too complex a task to tackle on my first attempt at circuit design. Then it suddenly struck me. What have we been taught over and over in this course? Engineering is about making things easier using abstraction. There are millions of these LED displays around the world, so this problem has already been solved long ago. There's a chip for that. And this is it. At least it's one of the many different chips designed to do this job. It's the MAX 7221. We don't have time for me to explain the chip in detail, but it's all in the datasheet. Basically, you connect up to 8 digits of LED display, a single resistor to determine how much current each LED will be driven with, and you send commands to the chip via its serial interface. Simple. So here's a breadboarded version of what I've explained so far. Here are the LED displays. This is the LED controller chip. We have our rotary encoder here, and here are the debounce circuits. This is the microcontroller board. It's just an Arduino, essentially the same as this one, but in a smaller package. Alright, so now I turn it on, the microcontroller boots up, and we can see the display showing 45. The software used here is simple. It just reads the encoder and increments or decrements the display depending on which way the encoder is turned. Using the LED controller also has the advantage that it manages power well. It doesn't turn all the LEDs on continuously, but only actually illuminates one digit at any given time. It cycles through the digits so rapidly that it appears to the eye that they are continuously illuminated. This limits the current the chip has to provide. Ultimately, this device needs to be portable and so has to run on batteries. So saving power was a very important consideration that dominated the rest of this design. Since this is generally a set and forget sort of device, it makes no sense to leave the display illuminated all of the time, since no one is likely to be looking at it while the timer is running. So we'd like the display to turn off once it starts running, but it also has to be easy to turn it back on in case the user wants to check how much longer it has to run. I could do this with a simple button, but my thinking was that a more elegant and a modern approach would be to make the knob touch sensitive. If it wasn't being touched, Then it would start an internal timer, and if not touched again when the timer ran out, it would turn off the display. Similarly, if the knob was touched when the display was off, it would re-illuminate. I did a bit of hunting around on the net and found that this could be done quite simply with a microcontroller. First, we connect a resistor between a digital output pin and an analog input pin on the microcontroller. If the output pin is set high, which is 5 volts, then the input will immediately read that 5 volts. But now consider this circuit. Now when the output goes from low to high, it takes time for the capacitor to charge, and so it takes time for the analog input to reach 5 volts. Human beings, of course, have capacitance, and so the time it takes to rise to 5 volts, which the microcontroller can be programmed to measure, will be different depending on whether or not the pin or whatever is electrically connected to it is being touched. I tried this on a breadboard and it worked. Sometimes. It worked sometimes, and at other times it didn't seem to work at all. After some experimenting, I discovered that it only works if the microcontroller is powered from a main supply, like a laptop computer connected to its power supply. If the power supply is removed and the laptop runs on its battery, then this ceases to work. The problem is, I think, that this technique assumes that the person and the microcontroller share a common ground. This isn't practicable for a device designed to run on batteries. This was a shame because I was really excited about the idea of building a touch-sensitive device, but the thought of trying to figure out how to get around this common ground problem wasn't something I felt confident about. But then the solution became obvious. I've seen a lot of battery-operated touch-sensitive devices, so this problem has already been solved. Yes, there's a chip for that. Several, in fact. Here's the one I chose, the Atmel AT42QT1010. The datasheet tells you a lot about how it works, but it's really just a black box with a simple interface. All it requires is a power source and a couple of external components to control sensitivity. I can't show you a breadboard version of it working because it is, unfortunately, only available in surface mount packaging. I found that a bit daunting as I'd never used surface mount before, and my eyes are not what they used to be. However, it turned out to be quite easy to work with, so I'd encourage anyone there that thinks surface mount is too hard to give it a go. You might be surprised. It also occurred to me that the Arduino boards I was using had a lot of hardware on them that I wasn't going to use, like the USB port, voltage regulators, and the power LED. I wondered how much power that was wasting. This Arduino is just running a simple program that flashes the red LED every few seconds. The multimeter is measuring the current going into the board, and you can see that it uses around 27 milliamps when the LED is on, around 25 when the LED is off. So the LED uses about 2 milliamps. Here's the same board but with one small difference. I've taken out the microcontroller chip. It's gone, but the board is still drawing 17 milliamps. If we allow 2 for the red LED, that means the rest of the board is drawing over 15 milliamps. That struck me as unnecessary waste, so I decided to get rid of the bits I didn't need. Here is a bare bones Arduino. I've got it running a program that flashes a LED just to show that it is functioning. As you can see, it's drawing around 16 milliamps, which when I remove the LED drops to 13. That's about half the current required to run the full Arduino board. There are a couple of other power-related issues to discuss, but I'll do that later. Now at this stage of the project, I'd finished the circuit schematic, so the next step was to design and make a printed circuit board, the first time I've ever done that, and then build the device. So here's the finished board. I power it up and, as you can see, here's the display and the encoder. I turn the encoder clockwise, the time goes up. I turn it anti-clockwise and the time goes down. The multimeter is measuring the current drawn by the board, and you can see that it's around 28 milliamps. If I let go of the knob and wait about 10 seconds, the display goes off and the current draw drops almost down to 16 milliamps, which is about a 40% saving. If I come back and touch the knob, the display comes back on and the current goes back up. Now, this device is designed primarily to time in minutes, but to give it more utility and make it easier to demonstrate, it has two modes that I can change by pushing the encoder down for more than 2 seconds. When I want to run the timer, I push the encoder quickly down and the display counts down the time. After about 10 seconds, the display goes out, but the timer is still running, and after the 15 seconds have elapsed, the buzzer goes off. Studying 6002 also gave me another way to save power. We learned that in digital electronics, the dynamic power consumed could be reduced, most effectively by lowering the operating voltage, but this has some limited use here because the LED controller I chose is probably old technology, in that it requires a supply voltage of at least 4 volts, so there's a little room for improvement. Next time, I'll be more careful. But another factor that influences dynamic power is clock frequency. Normally we would resist lowering that, but in this case it is a valid strategy to reduce power consumption. These Arduinos run at 16 MHz, which is far faster than required for such a simple application. The computation is low and the required timing accuracy is not high. So, this is the same board but with the clock frequency reduced to 1 MHz. The current draw is dependent on what's in the display, that is, how many segments are lit. If I turn back to the 15 we were displaying before, the current has dropped to about 16 milliamps. It still functions as normal, but when the display goes off, the current drops to 6 milliamps. A nice improvement. Well, that's the timer sorted, but I still need to decide how to power it. As I said earlier, I want to run it on batteries. Ideally, the battery would be small, so my first thought was to use a 9-volt battery, like the one on the left, and somehow regulate the voltage down to 5 volts. I always prefer rechargeable batteries when possible, but the 8.4 volt nickel metal hydride battery in the middle doesn't have a large capacity. I'd be better off with something like the much larger capacity AA batteries on the right, but then I'd need 4 of them to reach 5 volts. Ideally, I'd like to use just 2 of them, but that will only give me 3 volts for normal AA batteries and as low as 2 volts for rechargeable batteries as they lose their charge. Then I remembered this problem from Lab 9. We boosted an input voltage to a higher level by storing energy in an inductor. The switch is rapidly turned on and off by the square wave generator. When it's on, the current builds up in the inductor and stores energy. When the switch goes off, the inductor current can't change suddenly, and so its voltage rises until it pushes through the diode and charges the capacitor. 6002 has given us the knowledge to build one of these, but once again, why reinvent the wheel? This chip has the switch and oscillator built in, and even a feedback mechanism to control the output voltage. The oscillator has a fixed frequency, but the comparator, A1, can turn the oscillator on and off. When the feedback pin FB falls below 1.245 volts, the oscillator is turned on. When it rises above that voltage, the oscillator stops. By attaching the feedback pin to a voltage divider across the output, the chip will drive the output voltage at the level required to keep the pin at 1.245 volts. So here's a schematic of a basic power supply that can be used to produce 5 volts from a lower voltage input. The potentiometer needs to be set so that the wiper is at 1.245 volts if the output voltage is 5 volts. The most important design decision here is what should the value be for the inductor. If we want to provide a current I/O at voltage VO, then the power that the inductor must provide is given here. VD is the voltage drop across the diode. If we want 5 volts out but our diode drops 0.5 volts, then the inductor has to get the output to at least 5.5 volts. If this power is divided by the frequency of the oscillator, then we have the energy that the inductor needs to store in each cycle. The energy the inductor actually stores is given by this equation, where I peak is the current that is flowing in the inductor when the switch turns off. Now, we've been taught that this is how the current in the inductor changes over time when the switch is turned on, assuming there was no current to begin with. In this situation, R is the sum of the resistance in the switch and the DC resistance of the inductor coil. So if the switch is on for time t on, we can calculate I peak. The critical requirement is that the energy stored in the inductor must be greater than the energy required. It is not critical that these two values match exactly, because if the inductor provides too much energy, the feedback mechanism will turn the oscillator off, effectively lowering its frequency without changing T on. Okay, I've put all of this into a spreadsheet to help calculations. Let's say V in is 3 volts and we want 5 volts out. The drop across this particular diode is half a volt. Let's assume we want 50 milliamps. Not for this project, but it would be nice to have a power supply design that could be used more generally. According to the specs, the switch resistance is around 0.8 ohms. The DC resistance of the coil is about 50 milliohms. The on time for the switch is 22 microseconds. And the switch frequency is 23 kilohertz. The last two parameters are just to adjust the scale of the horizontal axis of the graph, which shows inductance in microhenries. In the top graph, the red line is the energy that the inductor can store per cycle, and the blue line is the energy required per cycle. So, as long as the red line is above the blue line, the circuit will function. The lower graph shows the same basic information, but expressed in terms of the current required and the peak current in the inductor. As you can see, anything in the range from 2 to 150 microhenries and beyond will suffice. However, we also want this to work when the input voltage is lower. At 2.5 volts, the graphs get closer together, but there is still a wide range of usable inductance values. When the input gets down to 2 volts, the two graphs now cross, suggesting that very low inductances and values above about 100 microhenries will not be able to provide a 5 volt output at 50 milliamps. I happen to have two values of suitable inductor in my parts bin, 47 and 100 microhenries. Either would suffice, but I have chosen the 100. That might seem a strange choice, but if you look at the lower graph, you can see that the higher the inductance, the lower the current running through the switch. Since the inductance and the switch both have resistance, it is more efficient to work with lower currents. The other consideration is that the switch current should not exceed the maximum rated current of the switch, the maximum rated current and saturation current of the inductor. So, here is the power supply on a breadboard. The small blue component is a trim pot that I use as the voltage divider. By turning the little screw, I can adjust the output voltage. The yellow multimeter is measuring input voltage, and the one on the right measures output voltage. When I turn it on, we have 3.5 volts in and 5 volts out. If I turn the input voltage down to 3 volts, the output stays at 5 volts. The same is true when I turn it down to 2.2 volts. or even slightly below 2 volts. So, the circuit works. Well, not really. Look what happens when I apply a load of 100 ohms, which should be drawing around 50 milliamps. Suddenly the output voltage drops to 1.8 volts. Even when I raise the input to 3.1 volts, the output only makes it up to 3.2 volts. So actually, it doesn't work. In the past, I would have given up at this point, but after 6002, I now have an understanding of how this thing works, so I was determined to find out what was wrong. I struggled for a while. I checked and rechecked the calculations over and over, but couldn't find any errors. Then, as I was thinking about how the circuit worked, it suddenly struck me. On the top end of this breadboard, there are a few wire connections. No components, just 5 jumper wires connected together via the breadboard. The multimeter is set to measure resistance. I zero the meter to eliminate the resistance of the probes, connect them to the wires, and get a value of 33 ohms. That's large. Pressing the wires to try to improve the connections reduces it a little. But there is still about 8 ohms of parasitic resistance in those connections. The switch circuit in the design has about half an amp running through it, so a resistance of just 1 ohm will waste 250 milliwatts. That's 50 milliamps at 5 volts, the total power output of the supply. Let's look at what effect adding extra resistance to the inductor connections would mean. As we increase the DC resistance, the required inductance increases. And by the time we get to 7 ohms, the chosen inductor will no longer work. If the input drops to 2 volts, then it only takes 1 ohm to make the inductance insufficient. And with just 2 ohms, no value of inductance will satisfy the equations. So, assuming this parasitic resistance was the problem, I built the circuit onto a PC board, and here it is. There are a few extra components on this board, and I'll explain those shortly. Here, the left multimeter is measuring input voltage, and the right one, output voltage. There is also a 200 ohm load attached, which should draw about 25 milliamps, which is appropriate for this project. When I turn the circuit on, we see 5 volts appear at the output. So when I turn the voltage down to 2 volts and turn it on again, we still have 5 volts at the output. The power supply works under load. This is the same situation, but now the right meter measures input current and the left one output current. So the power in is around 163 milliwatts and the output is about 112. That's only an efficiency of around 70%. That's not great, and I'm sure it could be improved by better quality components and layout, but I'm just happy that I got it to work. As I mentioned, there are a few extra components on the board that need to be explained. They relate to my final power-saving design element, turning the device off when it's not in use. I needed a way to manually turn the timer on and off, but the trouble with a conventional switch is that if you forget to turn it off, then the battery runs flat. I wanted to avoid that by having the device turn itself off automatically after a period of inactivity. At first that seemed difficult but I soon realised that 6002 had given me all the knowledge I needed to design a simple auto-off circuit. Here's my starting point. The battery is connected to the rest of the circuit through a P-channel MOSFET. When the on switch is held down, the MOSFET lets the current flow and the microcontroller boots up. After a little internet searching, I found a suitable MOSFET that had a low threshold voltage, so it would still work with depleted battery voltage, and a very low R-on of less than 60 milliohm. Of course, if the switch is released, then the power will be cut as the charge on the MOSFET gate leaks away. My idea was that the MOSFET gate could be connected to a microcontroller output pin, which would hold it low so that the power remained on after the switch is released. There are a few problems with this, but one in particular is that it would involve connecting a microcontroller output pin into a circuit that could, through pressing the switches, be forced high when the pin was trying to maintain a low output. That doesn't sound like a good thing to me. The solution is to buffer the microcontroller from the power circuit using an N-channel MOSFET. Here's the final circuit. The various resistors are there either as current limiters or as voltage dividers. R7 is there to make sure the gate never holds a charge and opens accidentally. When the device boots up, the first thing it does is set the gate on the N MOSFET high so that the switch can be released without losing power. After a suitable period of activity, the software needs only to set the gate low and the device turns itself off. Manual turn-off is available using the other push button that shorts out the 100k resistor and hence raises the gate voltage of the P MOSFET above the threshold and turns it off. So here is the finished device. Push the button to turn it on and it operates as normal. After 10 seconds, the display goes off until the knob is touched. To turn it off manually, just push the other button. If you leave it untouched for too long, it turns itself off. So, to anyone who's got this far, thank you for watching and for your patience. I haven't covered every detail involved in this project. To do so would make this video far too long. But if anyone has any questions, I'd be happy to respond to emails sent here. Thanks.